Hey, thanks for coming back. I was a little worried after the longness of the length of the last video. Sorry, there's nothing I could do. Today we're going to talk about families of functions. What are families of functions like? Do they fight? Okay, so different non-vertical lines have different slopes. We say non-vertical because vertical lines don't have slopes, because their slope is undefined. So, if they're not vertical, they have different slopes, or different y-intercepts, or both. Sometimes they have different slopes. Who knows? But they are graphs of different linear functions. For any two such lines, you can think of one as a transformation of the other. The transformation just means like, here's one line, we're going to move it around and twist it a little bit and move it over here, and it's a different line. Okay, so there are sets of functions called families, in which each function is a transformation of a special function called the parent. Linear functions form a family of functions. Each linear function is a transformation of the function y equals x. So y equals x is the parent linear function. The parent function is the simplest form in a set of functions that form a family. Each function in the family is a transformation of the parent function. One type of transformation is a translation, which slides the graph to the side or up, or to the side and up, which might look like diagonal. So a translation shifts the graph of the parent function horizontally, vertically, or both without changing the shape or orientation. For a positive constant k and a parent function f of x plus or minus k is a vertical translation. For a positive constant h, f of x plus or minus h is a horizontal translation. So let's take a look at what this looks like in graph life. Adding k to the outputs, so f of x is your output, x is your input, f of x is your output. Then if we add a number to it, we're sliding everything up. Or if we add a negative number to it, we're sliding everything down. F of x plus or minus h, if we subtract h from the input, the graph goes to the right. So that might be a little counterintuitive, that if it's x minus a number, we actually go to the right, which is the positive direction. And if it's x plus a number, then we go to the left, which is in the negative direction. So when we add to the output, it goes with the same sign. If we add a positive number, the graph moves up. If we add a negative number, the graph moves down. But if we add or subtract to the input, it has the opposite effect. If we add a number, it moves to the left. If we subtract a number, it moves to the right. So how are the functions of y equals x and y equals x minus 2 related? How are their graphs related? Let me think about that. So let's make a table of values. If our x values are negative 2, negative 1, 0, 1, and 2, y equals x, they're going to be the same. But y equals x minus 2, they're going to be 2 less. So what does that look like on a graph? Here's y equals x, and then here's y equals x minus 2. For each x value, the y value is just 2 lower on the second one. So it's shifted down 2 units. What is the graph of x squared minus 1 translated up 5 units? So this is x squared minus 1. The graph of x squared is just a parabola that goes through the origin. So x squared minus 1 is a parabola that is 1 down. Well, if we take that and move it up 5, 1, 2, 3, 4, 5, the vertex is only 1, 2, 3, 4 above the center. So another way to think about it is, if I translate up 5 units, I'm going to add 5 to the output. And so x squared minus 1 plus 5 is plus 4. Blah, blah, blah. Here we go. And you can check by plugging in points. And it's a wonderful exercise that you should do. that I won't right now. Okay, so pause it, see if you got it. Okay, so how are the functions y equals 2x and y equals 2x minus 3 related? So you could say that for each input, the output of y equals 2x minus 3 is going to be 3 less than the output for this one. And how are their graphs related? Well, y equals 2x is going to be a line that goes through the origin with a slope of 2. And y equals 2x minus 3 is going to have the same slope of 2, but it's going to be 3 units lower. It's going to be translated down 3 units. What a perfect drawing. Who needs rulers, right? Okay, so what for B? What is the graph of y equals 3x translated up 2 units? So we just add 2 onto the end. It's y equals 3x plus 2. Boom. Alright, so horizontal translations. So this graph shows the projected altitude, f of x, of an airplane scheduled to depart at noon. If the plane leaves 2 hours late, meaning instead of leaving at time equals 0, it's leaving at time equals 2, what function represents this transformation? Well, a 2-hour delay means the plane leaves at 2. This shifts the graph 2 units to the right, and that means we need to do f of x minus 2. So suppose the flight leaves 30 minutes early, so it'd be like back here. So these are hours, so 30 minutes would be half of an hour, so that's negative 0.5. So if it leaves 30 minutes early, what function represents this transformation? It would be f of x. Now since we're going backwards, it's going to be plus 0.5. The golden wedge. That's your secret phrase. A reflection flips the graph of a function across a line, such as the x or y axis. Each point on the graph of the reflected function is the same distance from the line of reflection. It's like a mirror. If you're 1 foot away from a mirror, then your reflection is 1 foot away on the other side of the mirror. Or at least that's what it looks like. Alright, so when you reflect a graph in the y-axis, so here's the y-axis, the x values change signs, but the y values stay the same. So here's the, look at this point. 1, 1. If I get reflected across here, it's negative 1, 1. It's still the same height, so the y value stays the same, but the x value changes sign. Instead of going 1 to the right, we're going 1 to the left. When we reflect across the y-axis, or the x-axis, man, I'm talking weird. When we reflect across the x-axis, the x values stay the same, but the y values change signs. So look at these 2 points. 1, 1, 1, negative 1. The x value stays the same, but the y value changes signs. So for a function f of x, the reflection in the y-axis is f of negative x, and the reflection in the x-axis is negative f of x. So reflecting on the y-axis changes the sign of the x value, which is the input. Reflecting in the x-axis changes the sign of the output, which is the y value, or f of x. So let's let g of x be the reflection of f of x equals 3x plus 3 in the y-axis. What is a function rule for g of x? Okay, so for a reflection in the y-axis, we change the sign of x. So g of x equals f of negative x. Evaluate f of negative x and simplify. So f of negative x, so f of something equals 3 times something plus 3. If we're doing f of negative x, we're going to do negative x in there. So 3 times negative x plus 3, so that's negative 3x plus 3. So you can check by graphing both of them, and bada boom, you'll notice they have the same y-intercept, which is the 3, but it's a reflection. in the y-axis. Okay, so let h of x be the reflection of f of x equals 3x plus 3 in the x-axis. So this is 3x plus 3, this black one. If we reflect it in the x-axis, it's going to look like this. And again, who needs a ruler when you can draw straight lines like this? Okay, so remember that reflecting across the x-axis changes the sign of the y value, which is the f of x. So we need to do negative f of x. So f of x is 3x plus 3, so we need to do negative of 3x plus 3. Let's see. H of x is negative f of x. So h of x equals negative 3x plus 3. And the multiplicative property of negative 1 tells you that this is a negative 1 that you distribute. So that's negative 3x minus 3. And that makes sense with our graph. We have the same slope as the blue line, negative 3, but our y-intercept now is down here at negative 3. Pretty cool, huh? A vertical stretch multiplies all y values of a function by the same factor greater than 1. A vertical compression reduces all y values of a function by the same factor between 0 and 1. So you're basically, when you're stretching or compressing vertically, you're multiplying the y values by a number. If that number is between 0 and 1, then your stuff's getting smaller. If you multiply by a number bigger than 1, then your stuff's getting bigger. So for a function f of x and a constant a, y equals a times f of x is a vertical stretch when a is greater than 1, and a vertical compression when a is between 0 and 1. Okay, so the table at the right represents the function f of x. What are corresponding values of g of x and possible graphs for the transformation g of x equals 3 times f of x? So this is going to be a vertical stretch because we're multiplying by a number bigger than 1. So we're going to multiply each value of f of x by 3 and find each corresponding value of g of x. So we're just going to take this table. This table is just this, copied over here. And now 3 times f of x is just 3 times whatever we got here. So 2 times 3 is 6, 2 times 3 is 6. Negative 3 times 3 is negative 9. 1 times 3 is 3, and negative 2 times 3 is negative 6. So let's draw simple graphs for these things. We got in blue here, or in red is our original f of x. Okay, we had negative 5, 2. Then we had negative 2, 2. Then we have 0, negative 3. And then we got 3, 1. And then we got 5, negative 2. So then when we did 3 times f of x, the x values stayed the same, but our y value got 3 times further away, right? So we got negative 5, 6, negative 2, 6, 0, negative 9, 3, 3, and 5, negative 6. Okay, so let's see if we got this. For the function f of x shown in problem 4, so that is this guy right here, what are the corresponding table and graph for the transformation h of x equals 1/3 f of x? Alright, so here's like an enlarged version of our graph. Here's f of x. Timeout. I want f of x in red. Okay, so now let's figure out h of x. So h of x is 1/3 of f of x. So 2 times 1/3 is 2/3. So my new point here is going to be negative 5, comma, 2/3. So right about there. Back 5, up 2/3. Not quite 1, but more than halfway. Alright, so for 2, negative 2, we're going to do the same thing. 2 times 1/3 is 2/3. So we get the point negative 2 2/3, which is right there. For 0, -3, we're going to do 1/3 of f of x, so that's -3 times 1/3, which is -1. So we get the point 0, -1. Boom. For 3, 1, f of x is 1, so we're going to do 1/3 of f of x. So that's 1/3 times 1, which is 1/3. So we get the point 3, 1/3 over 3 up 1/3. And then when f of x is -2, it's going to be -2 times 1/3, which is -2/3. So we get the point 5, -2/3, which is over 5 down 2/3. Then we can fill in these cool lines. And here we have our graph h of x, which is a vertical compression by a factor of 1/3. So here is a nice little concept summary. This would be a good thing to have in your notes. I would say that. Good thing to have in your notes. You noticed that before? So transformations of f of x. So vertical translations. Up k units, k is positive, f of x plus k. Down k units, f of x minus k. A vertical stretch, if a is bigger than 1, a times f of x. Vertical compression is a times f of x, but a is smaller than 1 and bigger than 0. Horizontal translations. This is actually, these two are the ones that are a little bit trickier. A translation right h units is going to be f of x minus h. So this is the one that's weird. To the right, which is normally positive, you get a subtraction. Translation left, which is normally negative, you get a plus. And then when you're reflecting in the x-axis, y equals negative f of x. When you're reflecting in the y-axis, y equals f of negative x. You can remember this as when you're flipping across the y-axis, the value of x is the opposite. And when you're flipping across the x-axis, the value of y is negative. So y equals f of x, so negative. Okay, so combining transformations. The graph of g of x is the graph of f of x equals 4x compressed vertically by the factor of 1/2 and then reflected in the y-axis. What is the function rule for g of x? Okay, so we're going to compress f of x by the factor of 1/2. That means we're going to multiply f of x by 1/2. So 1/2 times 4x is 2x. Next, we need to reflect across the y-axis. When you reflect across the y-axis, the x coordinates change sign. So it's going to be 2 times negative x, which is negative 2x. So the function rule for g of x is g of x equals negative 2x. What transformations change the graph of f of x to the graph of g of x? Okay, so let's see. How do we get from 2x squared to 6x squared minus 1? Well, it is 3 times 2x squared minus 1, right? So this is our f of x. So we're multiplying it by 3, which is a vertical stretch. And then we're subtracting 1, which is a horizontal shift down. So the graph of g of x is f of x stretched vertically by a factor of 3, then translated down 1 unit. All right, why don't you pause and see if you got it? All right, so the graph of g of x is the graph of f of x equals x, stretched vertically by a factor of 2, and then translated down 3 units. So what's the function rule for g of x? So g of x is, so we start with our f of x, stretch it vertically by a factor of 2, that means multiply by 2, then translate down 3 units, that means subtract 3. So there's our function rule for g of x. And then B, what transformations change the graph of f of x equals x squared into the graph of g of x is x plus 4 squared minus 2? All right, well, the plus 4 in there with the x, that is a horizontal translation. 4 units. Now, is it to the right or the left? This is the one where the sign is the opposite of the direction you're moving. So since it's positive, which is normally to the right, it's 4 units left. And then minus 2 is a vertical translation 2 units down. So we're going left and down. Okay, so there's your little introduction to transformations. Start on practice 2.6. Let me know if you have questions via the email, and I'll see you soon. Ta-ta.